Hi all, in this lesson we'll be talking about two more rules of calculus arithmetic, how to take powers and how to divide functions. So let's just hop into it. So with powers, in the beginning we saw that taking the derivative of x squared was 2x because we can sort of, take these little side pieces and throw away the corner. How about x cubed? Well, we can visualize it in a similar way, right? So we have a cube and we're sort of adding plates to the side. So we have three sides, or x times x times x, so we have three dimensions, and we add a plate to each side and we kind of thicken it up. And we get this sort of, boxy shape. And again, the gutters are similar to this. It's things that are interactions between the plates and we want to ignore them. And that should sort of give us a hint about how x cubed will grow. And our guess would be 3x squared, right? It's x squared plus x squared plus x squared. And yeah, that's right. Now, this is kind of cool. We figured it out, but one, it was visual, which is kind of nice, but we don't want to actually have to visualize everything. So if I talked about the 5th or the 10th or the 15th dimension, it's pretty tough to figure out what's going on. So we want to be able to use algebra to make these shortcuts work, and we don't have to rely on visualization. Again, it's a great starting point, but at some point we reach the limit of how useful it can be. So let's think about the algebra for a second. Ooh, it's getting a little bit gnarly. If we take x plus dx cubed, we have to cross multiply all this stuff out, and it gets really nasty, right? It's just more and more terms, and we're kind of getting stuck in the algebra. And there are shortcuts. You can use the binomial theorem and things like that and try to count how many pieces we have, but let's just step back for a second. What's actually going on? Can we use our intuition a little bit? And we can. So the essence is that we just have three interacting parts. We have three sides, let's just call them A, B, and C, and they're all interacting. They're all going to contribute to the whole. And now it turns out all the sides are equal, but let's just stick with it for a second. So we have three parts. They're all sort of interacting. They're all adding changes from their own perspective. A thinks that when he changes, the other two guys are staying still. So he's going to add dA times B times C, right? Because A thinks I'm changing. The other guys are staying still because we don't have any crosstalk, no interactions between changes. I'm the only guy changing. The other guys are staying still. So it's my change, dA, times B times C. And the other guys think the same exact thing. B thinks that's my change, dB times A times C, and C thinks it's my change, dC times A times B. So when we add up all these viewpoints, we get this little, jumble of arithmetic here, or algebra here. And then we know that we can actually plug in x for all of them, because all of the guys started as the same thing. We call them A, B, and C, but they were really just different labels for the side x. So dA is dx, and A, B, and C are x. So plugging that in, we can see that we get 3x squared. So the reason we want to think about it in these terms is we can kind of understand how the rule is being formed. I mean, at the top level, you can say, okay, it looks like we just dropped down the exponent and subtracted 1, and we get 3x squared. And, that's a good shortcut after you know how it's working. And we finally do know how it's working now. It's because every side thinks he's the one that changes and the other guys are staying still. So we're going to lose a dimension because one of the guys is turning to dx and the other guys are staying still. And how many perspectives do we have? Well, we start with 3 perspectives, so we'll have a 3 here. That's why there's a 3, because it's A plus B plus C, so there'll be 3 parts. If we had 8 perspectives and we take the derivative, well, let's say x to the 8th, we'd have 8 components to take care of, and each of those, one of them turned into dx, so we have x to the 7th left over. And that's how we'd get the derivative of x to the 8th power would be 8 times x to the 7th. And eventually, again, you can memorize that as a little shortcut, a little rule, but think about what's actually happening. Think about the perspectives that are being added, and it'll make a lot more sense. Okay, so now we can actually try to work backwards into the integrals of powers. So if I say, well, I have all these steps that were coming in of size 3x squared, what do they assemble into? Well, we just worked it out up here, right? So we know we can work backwards by the fundamental theorem of calculus. We can work backwards and know that 3x squared really came from x cubed, or one of its cousins, right? X cubed with some constant. So that's sort of the general pattern there. Now, if we kind of don't want to do trial and error all the time, we can sort of get a general approach. Let's say, how about the integral of plain old x squared? Well, one little trick is we can say, hey, x squared is really the same as 1/3 times 3x squared, right? It's just 3 copies of 1/3. And now this is kind of a friendly version that we can actually integrate. So then we can basically plug in the integral here and get 1/3 x cubed. So as you practice calculus more and more, you'll kind of learn these tricks where you can sort of predict what general shape will be happening. So if you see an x squared and you integrate it, you know there'll be an x cubed involved, and you know that 3x squared, for example, is a friendly thing to have. So we try to rewrite it a little bit and make the math a little bit easier. So again, these are things that it takes a little bit of trial and error work to do. When you start, you're sort of learning where to factor things out and where to multiply things, and you'll get better and better. But it's okay because, again, you know how to be the antique stealer. Remember, the antique stealer, when he saw a pile of shards, he just made a guess and broke it and kept going until he found the match. So when you're trying to work on an integral, just think about what general shape it could be, and then start breaking a few vases and see which one actually works out. You don't have to get it on the first try. Eventually, you'll learn how to do it, but in the beginning, just try a few approaches. Now, the last thing here is the derivative of powers. We saw before that the derivative of an inverse, 1 over x, was negative 1 over x squared. But then how about the derivative of a division? So it's f over g. How can we kind of derive that? Now, I don't actually like this rule because I think it's kind of cumbersome, but we're going to go through it just because you're going to see it everywhere, and we'll have kind of a shortcut to help make it easier. Instead of seeing a division as a division, just see it as multiplication. F divided by g, well, it's a times b, where a is f, and b is actually 1 over g. So we kind of bundled up 1 over g, and we called it b, and now we have what looks to be a multiplication. And we can do our multiplication rule out, and then we get dA times b plus dB times a, and then we can kind of plug things back in. And this is where we know, okay, if b is 1 over g, the derivative is following that same pattern there, negative 1 over g squared. We can multiply both sides by dg, so we get dB, just that total change, is negative 1 over g squared times dg. And then we can plug that in, and then we can get a rule like this. The quotient rule, again, I don't like it. If I have a quotient and I need to take the derivative, I'll just do a little trick like this and pretend it's a multiplication, work it all out, and then plug back in. If you like, you can try to memorize it, and you can rearrange it like this, like a lot of textbooks do. But again, I think it's just, basically it's a torture device designed to make students think that they're learning calculus when they're just memorizing things that don't really matter that much. If you can do the product rule pretty well and you know how to do the inverse, then you can plug in when you need to. So with me, with that, that's sort of my high-level intuition about how the quotient rule can be used. Now, this is sort of the final lesson in terms of finding out the rules. There's a few practice problems in the actual article, and then next week we'll be able to start taking our knowledge and applying it to that Archimedes scenario in the beginning, where we're trying to turn a circle, from a ring all the way into a sphere. Happy math.